on to the main course.
Oh, all right. So we have devils. All right, guys. So, if I remember correctly, the last time we developed this formula, and if you haven't been to class in a while and you haven't watched the videos, none of this is going to make sense. But if you at least know about the x bar plus or minus z sigma over square root of that one for confidence intervals, that's got the same form, yes? And we went through the derivation of where this formula came from. It does the exact, has the same goal as the first confidence interval formula we created. It's taking something we see from a sample and kind of improving on it, giving a range which communicates something about how certain we are about what we found. Let me stop for a minute. Right? So if I measured something and I got 20 and I said give or take 1, that seems pretty good. If I measured and got 20 and said give or take 10, I'm like, you're not really sure about what you got. You guys are gonna with me? Yeah. And you guys also now understand something that you actually had a feel for before. You know that taking a larger sample is better. But now the math is finally catching up to us. What was this piece of the formula called?
The error.
The error. And that sounds like something I would want to make small.
So the right is the error?
Say again?
The right, for the...
This piece.
Okay.
I'm sorry.
No, it's fine.
If you're at home, no. For those of you at home, this piece. I'm sort of, maybe I should, it doesn't matter. Let me do this, because they do a lot of shit up here. And for some reason, this is here now, so. All right. Okay, so if I make my sample size bigger and I just make that change, that's gonna make this smaller. Are you guys with me? Okay. And if I make that smaller, my confidence interval becomes narrower. I'm now communicating that I'm more certain about what I found. Okay, I like it. Okay, so let's try some of this stuff out. If you need a calculator, come on up and grab one. Bring me something. Bring me tribute. Thank you. Make sure your calculator turns on, has enough battery. Let me know if it doesn't. I haven't checked in a while. Okay. So, first thing I want you to notice. We want, well, first, all right, let's do all this first. P hat, the little hat on the P, tells me it's coming from a sample, right? So, what's the difference between mu and x bar? Mu is the population mean. X with the little thing on its head, the bar, is the sample mean. So here, for percentages, it's very similar. P by itself would be a population percentage or probability. P hat, the little party hat, that means it came from a sample. Kick ass. So I've got a formula sitting there, but the formula almost, as always, the formula almost makes it worse than it seems, than it should be. Can somebody tell me how many out of how many in our sample did what we're looking for?
459.
459 out of?
652.
That's the percentage. So go ahead and try to calculate what that is. Don't say anything.
Professor,
Yes.
I need an extra worksheet.
Sure. Anybody else need this worksheet?
decimal places?
Good, exactly. So, oh, Jeff. Come on, old man. Alright. Shit. Alright. 459 divided by 652. No, Jeff, 459 divided by 652. There we go. So what should I put down here?
704.
Good. 0.704. So for percentages like this, for p hat, q hat stuff, I want at least 3 decimal places. So like I said last time, you can make everything 4 except for z-scores. Everything 4 places. Z-scores only 2 because our chart only goes to 2 places, yes? If you do that, your ass is covered. Right? And generally it's good. What's q hat then?
652 minus.
No.
Oh, 1 minus 7.
Yeah. No, what you're about to do is fine, but it's more work than you have to do. It's got to be the rest percentage-wise, right? So it'll be
296.
0.296. Is everybody cool with where that came from? Okay. Sorry? The 0.296? Alright. No matter what clothing they're wearing, what does P and Q have to add up to be?
652.
100%. 1. So if P hat's got 0.704, Q hat gets the rest. 1 minus 0.704. Hey, now we're filling up. Okay. A few more people just came in. Does everybody have this handout from last time? Let me know if you don't. Okay. So we did this side last time. Look at all that work we did. Look at us go, look at us go. And now we're doing this side. This is kind of silly, but what's n?
652.
Good. Do you see how the biggest mistake I see in this kind of problem is people put 459 there? But n is always got to be the bigger number. It's got to be the total number of things you're looking at. The 459 is just what you saw out of those things. Yes?
So P is like the probability would happen, right? Because we're finding the probability that would happen.
Yeah, you either can look at, because a probability is essentially a percentage of, so like if 11% of you guys are left-handed, then there's an 11% chance I'm going to pick a left-handed person.
Right.
70.4% of my sample said they voted, or I can look at it as I have a 70.4% chance of picking somebody from the sample that voted. They both actually mean the same thing. Kick ass. Yes?
I think I missed how you got P.
Oh, the p hat part? All right, look at the sample real quick. Can you make a sentence that goes like this? This many out of this many did something. What would you say? How many out of how many? Sorry to put you on the spot.
No, you're okay. Just waking
You're good.
up.
How many total people did we talk to?
6.
Good. Out of those, how many did what we're looking for?
96. No, 459.
Yes, 459 of them. So 459 out of 652. If you do the math, divide it, you'll get 0.7. Is everybody with me? Yes. Oh. No, be careful. Of doesn't mean divide. And it's not Matt's fault, it's just English is weird, right? If any of you guys learn English second, you know in fact, those of us who learn English first, we could probably agree English is weird. Yeah. Of generally means multiply in mathematics, but that of is really part of 459 out of. It's just that English allows me to truncate that phrase, you with me? So it should be 459 out of the 652. And that's divide, right? Is that okay? So of means multiply in mathematics. English is weird. That's just the truth. So if I said I talked to 80 people and 14 of them like lasagna, what's p hat? I talked to 80 people and 14 of them like lasagna. 14 divided by 80. 14 out of 80 did something. Okay. So these problems, by the way, real quick. How many sentences did it take for me to tell you everything you needed? 2. Percentage problems. When I'm doing confidence intervals for proportions or percentages, it feels like I don't give you enough information because I don't need a ton. We don't need a lot of information. If I have what I need to figure out p hat, which means I have to be told n, and if I know p hat, I know q hat, so I actually don't need to give you a lot to get everything you need for this formula. So they're gonna feel like, did I get enough information? Yeah. Oh, okay, here's of course, Jeff. Sorry, without fail, I forget this every semester. Do you see what comes next?
MP.
Yeah, okay. That was neat. So, little side note. Let's see. There we go. Perfect. Yes. Okay. I don't know if you guys remember, and I didn't bring it with me, of course, because I'm just that good. But a while back, I gave you a sheet that had this big histogram. It was like related to flipping a coin.
Yeah.
And it was flipping a coin 14 times. So of course the highest bar was on 7 for the number of heads I was expecting to get, because it's 50-50, yes? So expect to get about half of them as heads. Are you guys with me? Do you see how the tallest bar is in the middle? Can somebody describe to me visually how you could tell something's a normal distribution?
Oh yeah, makes it better.
Makes a bell. What does that mean? Be a little more specific. As you go, a bell means in words it starts low, goes high, comes back low, yes? Are you guys with me? So this is all a side note here, by the way. This was when I flipped a coin 14 times, and the probability of getting ahead was a half, yes? You guys with me? What if I had a weighted coin where I weighted it so that the percentage, the probability of getting ahead was 0.01? Are you guys with me? So I weighted the coin, so it should be really unlikely for it to land heads. I weighted it in such a way that almost all the time it's going to end up tails. Yes? How did I get 7 on the first example up there? Where'd 7 come from? Why was that the most expected thing? It's the mean. And what was the formula for the mean?
Divided by 2.
No?
Oh.
What percentage of coin flips, if it's a fair coin, should I get a heads?
Yeah.
50%. And if I flip it 14 times, what percentage of those times should I expect a heads? 50%. 50% of 14, NP, yes? N times P. If I weight the coin so that 99% of the time it's not heads, it's tails, 1% of the time it's heads, what, if I flip it 14 times, how many heads do I expect to show up? How do I get it? No. The probability is now 0.01. I weighted it.
Oh.
It's not half the time I get heads. It's 1 out of 100 times I get a heads.
Okay.
14 times.
Yes. Oh man. My pen died. No. Hold on. Sorry. Pen. Okay. What is N times P now?
14.
Yes. I should expect to get almost no heads. If I flip a coin that has been weighted so that heads only shows up 1% of the time, I basically am going to expect about 0 heads. Yes? It only shows up 1% of the time now. Are you guys at all with me? Where should the highest bar be now if I'm going to graph this again? Why was the highest bar in the first one on 7? Why was the highest bar around 7? Because that was the expected value, correct? That's the expected number of heads.
So now
What's our expected number of heads now?
0.14.
So where should the highest bar be close to now?
0.14.
0.
Yeah.
Yeah? So now it's gonna start like this. Does this have any chance to be normally distributed?
No.
It's dead on arrival, yes? Are you guys with me? Yes. So, what if, so real quick, why is this normal? Because it has room to go up and room to come down. Does this have room to go up?
No.
It's middle, it's what should be in the middle is first. And I'm like, shit, I didn't have I'm up here already. I'm never gonna be normal. So, the Jeff realizing stuff about himself. Okay. So what if instead I had weighted it so it comes up heads almost all the time? What would the average be now? 13.86, I love it. So now where should the highest bar be close to? 14. Is there anything that I'm gonna get above 14? Is it possible to get more than 14 if I flip the coin 14 times? No. So that's another wall here, yes? And my highest bar is gonna be here. Now it's got room to go up. Does it have room to come down? No. Okay, so you get the general idea is if I have a binomial situation, I have a minimum number, 0, and a maximum number, whatever n is. If I want it to be normally distributed, I need the mean to be in the middle somewhere. So it's got room to go up and room to come down. So what we have determined, in kind of a way it's related to n greater than 30, remember that big hit? Is we have determined in order for a binomial to be roughly normal or to be normal enough, we need NP and NQ to be at least 5.
At least.
If they are at least 5, I've got room from 0 to go up. The NQ is kind of like the other wall. I've got room to go up and room to come down. If either one of those is not true, it's not normal enough. I can't do shit in stats 1. If we had a stats 2, we could do some shit. But at Grossmont, we can't do shit. We don't have a stats 2, I'm sorry. Maybe someday. Are you guys at all with me?
Yeah.
This is the replacement. N greater than 30 is when I'm talking about means. This check is when I'm talking about percentages. Go ahead. So if this checks out for a given situation, I'm allowed to use the z-score chart. If this doesn't check out, then for us, we can't do shit. I love you guys. Now on this problem, somebody remind me what P means? For a what? From a what? Versus this. Yes, from a population. And this is from a sample. On the problem we're looking at right now, do we have any clue what the true proportion is for everybody? What the population percentage is?
No.
No. So what's the next best thing? P hat. If I don't know the population parameter, I'm going to use the statistic. I'm going to use the sample, right? If I don't know mu, what's the next best guess? X bar. Yes?
Taking a few turns.
Would you multiply n against p hat?
And against Q hat. And we can't do NP and Q because we don't know P and Q, but we use the next best thing. So when I say check NP and Q hat, it's exactly the same as you going n is greater than 30. That's for a means problem. If n is greater than 30 for a means problem, what are we allowed to do? If n is greater than 30 for a problem about means, what do I know about the distribution?
Oh,
It's gonna be normal.
Normal limit. This is not a means problem, is it? Can't use that shit. Central limit theorem is for means. So now I need a replacement check. I can't say n greater than 30 is good enough. I need this to be true. This is the replacement. This is the check to make sure it's normal enough. Okay, I love it. You guys are like, this is too much for Tuesday morning. Yes?
Right, so if you don't know P and Q, use the.
P hat and Q hat. This is exactly what we did before. If we don't know mu, what do we use? X bar. That's what we did with confidence intervals. Yeah. If I don't know sigma, what do I use? S. Because if I don't have a clue, but I've got a sample, I do have a clue. I have somewhat of a clue. So I use the sample estimations if I don't have the actual numbers. Yes, that's basically what stats is. Almost all the time we don't have a clue, which is basically the definition of a human. We just don't have a clue. So then we try to get a clue. We get a little sample. Oh, I've got a clue. Okay, sorry. So, can you guys take a moment? I want to show you a shortcut for this kind of problem, but can you check n times p hat and n times q hat? What are they supposed to be? At least 5. Do you have this handout from last time?
I think so.
The one about the dolphins and such?
Yeah.
Okay. We're just working on the other side. So what'd you get for NP hat, anybody?
4.459.008.
Yes. Yes. Does that number show up somewhere else if you round it?
Oh,
So real quick,
I see.
if P hat is the number of successes divided by n, what's n times P hat, the number of successes? Do you have to know that? Does that have to make sense? No, you could do this shit, yes? But I could have done a shortcut and just said it's this.
Right.
Does that do what it's supposed to do?
Yeah.
What is it supposed to do?
Greater than 5.
Greater equal to 5, check. What's NQ hat? Somebody else.
192.992.
Do it again.
192.992.
192.992. Sounds not quite right, I don't think. Let's see.
That's what I got.
Is it?
That's what I got.
Oh, I'm doing it backwards. I'm sorry. You're fine. And that's at least 5. So when you do n greater than 30, you know it's approximately normal. When you do NP or NP hat, NQ, NQ hat, those kind of things, and you get at least 5, you know it's approximately normal. Same idea. I just have to have a different check for a different situation. Now I'm allowed to do the next step. What part of what I've told you gives you what you need to figure out what the z-score is for this?
96%.
Yes, and again, why? What does z-score tell you?
How?
The number of standard deviations for the.
So in general, if I want to truncate that, it tells you distance. How far? How far do I have to go to get 96% of the data? You with me? So if I tell you how confident I want you to be, why does that translate to a z-score? Because now I just got to figure out, okay, how far do I have to go to catch that lunch? Is that on your little baby chart? Does anyone not know what I mean when I say baby chart? There's a little baby chart. If I want to be 90% confident, blah, 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 it gives me the z-score. It's just a little shortcut. I am a math teacher, so therefore I am evil. So every now and again, I'm going to give you something that's not there. Do you guys remember how to find the z-score? Can you draw a 96% confidence interval?
Yeah.
What's going to be true about it?
The middle.
In the middle, I'm going to catch 96%. So how do I translate that into z-score? Bless you. That tells me how far to go up and down.
4 divided by 2.
Yes, yes, okay. So 96% inside, 4% outside, 2% on that side. I want to look up 0.02. Don't look up 0.02, no, 0.02 in the body, right? That's where the areas are. You can make whatever sound effects you want. So what z-score do you guys get?
-4.
2.05.
Oh shit. Wait. How?
Ruh-roh. 0.02, yes? The closest I can get to 0.02 is right there.
Yeah, I get you.
Okay.
I looked point two, not point oh two.
I'm not finding it random.
No, but like, I thought you were going based off like these numbers at the top.
No. Okay. 96 is a percentage. Do you agree it's an area?
Yeah.
So 4% is the other part of the area. Yes? So 2% is the area here. I can't look here on the chart because those are z-scores. I don't have a freaking z-score. I got a freaking area.
We're looking for Z.
So we got to look for the area in the body. Right? One of the most evil things about z-scores and areas is that they look the same. 0.02 could be an area, could be a z-score. I just have to know from context. Yes?
Did you put 2.05 Z?
Yes. Why did I put negative 2.05?
Cause plus minus.
Plus and minus is built in. So again, the formula has a plus or minus in it because the idea of confidence intervals is go up and down so much to catch this much data. If I catch 96% of the data, I am therefore 96% confident that I caught anything. So how confident would I be that I caught the true percentage of the whole population? 96% confident. Because I'm 96% confident I caught anything. Right? That's a weird example I gave about throwing the net out, catch 96% of the fish. How confident are you that you caught Billy, the fish that has evaded you for years? You're 96% confident you would catch Billy. And Billy's over there just laughing at you. I'm like, damn it, Billy. Sorry. Okay. So listen, the NP hat, NQ hat is new. Yes? That is the only part of this that's new, besides, of course, this guy. This guy we derived, it's got to be on your formula sheet. And now you just have to plug and chug. So what's P hat? 704, give or take. Z, 2.05, that's related to going up and down so much. Big ass square root. 704 times 0.296 divided by n, 652.
So you would plug all that in at the same time, right? Except for
I
that,
mean-
except for that other.
So again, I would do the 2.05 part first. Get what the error is first.
Oh, so you
Just like we did last time.
I moved ahead, but I have a question. Shall we?
Yeah. So there's always at least two levels to a math problem. There's the concept and there's the nuts and bolts, plugging shit in and so forth, yes? You're gonna have the formula. Plugging shit in is gonna be relatively easy. You just have to make sure you get all of the parts correct, right? If you calculate p hat and you get 1.38, does that seem good? P hat and you get 1.38. Does that seem good? What's the highest p hat can be? I see what you mean, but 1. Could be a 100% chance of something, right? So just be really careful. It's very easy to like divide the wrong way. And people just sort of like brute force forward and you get some weird ass shit. So just really make sure that everything's kind of making sense as you're going. P is a probability. It can be at most 1. For example. Okay.
like, would you put it in? Not put it like that.
What? Oh. Oh, I see. I think I see what you. Let's see.
Cause you multiply 0.704 times.
So you ready? Here we go. I'm gonna calculate this error first. 2.05 times square root 0.704 times 0.296, dadgummit, divided by 652. I'm just gonna put that. This calculator costs enough money. I'm gonna let it chew on all that shit. Yes? So I'm gonna calculate the error first, just like we did before. Is everybody cool with that? We already talked about, I don't know if everybody has one, the square root gets bigger. That's really nice, because then you can make sure that everything's in the square root that needs to be. If you have the square root that's got a little parenthesis, just make sure you don't close the parenthesis until the end. So you make sure all that stuff is inside. Are you guys? Because the next level of mistake people make is they put it in the calculator not right. So let's see, we all get the same thing. I get this. Ruh-roh. So if you didn't get that and you can't figure out why not, let me know. Okay. So what's that? What's that number mean? What's it doing? That's the error. So we think we're off by 3.66% at most. Do you remember how I told you if you pay attention to any polls, they'll say 48% are going to vote for this proposition and 40% are going to vote against it, and at the bottom it's going to say plus or minus 3 or plus or minus 4%. There's that shit. There it is. If I round it, that's plus or minus 4%. Yeah? So this will be, does anyone remember, does anyone remember the error, how I've got to write it?
One more decimal and
Yeah, one more decimal than what's here. So it'll be 0.0366, yes. So that is, we believe, 70.4% of voters voted, give or take 3.66%. Does that sentence I just said make sense? So you've heard people say this. How many people do you think is coming? 30, give or take 5. Yes, you've heard this all the time. That's based on kind of subjective understanding of the people that are coming and how likely it is that, what, you with me? This, you can see the freaking math that goes into it. If I wanted to decrease my error, what's the most immediate thing I could do? Get a bigger sample. You with me? What's the other thing I could do if I didn't feel like getting a bigger sample? I can lower my confidence level. Do you see how that is not preferred? Sure, you'll make your confidence interval smaller, but now you're less confident. That's bad. So the more preferred way to lower an error is to get a bigger sample. And day one, you guys knew that shit. Without knowing the math behind it, you knew a bigger sample is better. It just makes sense. And now the math is finally going, oh yeah, human, I agree. Looks good. Okay, maybe. So what's the interval then? 6, 6, 7, 4, up to. Yeah, I like it. And that's just adding and subtracting the 0.0366, yes? So take a minute and see if you can write the conclusion. Let me catch up to you. We are 96% confident
The interval,
that the interval.
67 registered voters.
No. We'll say 66.7%. These are percentages, right?
Oh, yeah. But when you round, oh, yeah.
To 74.1%. Does what? What do you think that interval does? 66.7% to 74.1%. What is it supposed to do? What's that interval supposed to do? Create it to go out and
Contain the true proportion of people that voted.
contain or catch. So you could say contains or captures, contains the true percentage of all voters. Voters who voted. This is how they do the polls. They do call people. They call normally somewhere between 1,000 and 2,000 people. They put the poll together. They tell you what percentage you're going to vote. But at the bottom, they have the plus or minus 3 or plus or minus 4%. It's almost always that because with the sample size between 1,000 and 2,000, that's how the error kind of comes out normally. Yes. Say again. That's fine. Yeah. Mathematically, I want this one to be one more place than that one, so I'm not rounding too much. But then after you get these numbers, you can round it back to how big this guy was. I have no idea if what I just said makes sense. You don't have to round it. You could have done 66.74%. That would be fine. Yes.
Tell me if this is wrong, because this is what I wrote. Okay.
Sure.
I got whatever 66.7 to 74.1 will catch the true proportion of people registered to vote that actually voted.
Yeah. Beautiful. So the way I wrote it is not the only way you're going, because that's English for you. You must have this. We are this and such confident that this interval captures the blah, blah. Yes? And what I tell people normally is what I say here is I'll say contains the plagiarize. Contains the true proportion of people that voted. Yes? Now, I did not just say plagiarism is good. I just said I'm supposed to report that finding. So of course you can just use the exact same language because that's what that represents, right? So yeah, if you're like, what the shit do I say here? I already told you what to say. Go copy it. That's what the interval is supposed to do that you created. Okay, maybe. More side notes, of course. Someday I'll do all of it at once. Which part of this formula, don't even write this down. I don't know if you can see this. Which part of this formula is the error?
Z to whatever.
All this Z crap, yes?
Yeah.
Okay. So remember how we did this before to figure out the formula for sample size? So if I know how small I want my error to be, I can see how big of a sample it's going to take. Yes? I call it a feasibility study because we can see is it feasible? If it's 800, okay. If it's 80,000, no. So if I solve this for n, and I'm not going to take, let's see, square both sides. I'm going to multiply the n up. I'm going to divide the e down, and I'm going to end up with this. That was a little fast. But that's just the algebra. I square it because there's a big square root by n, and then I have to multiply the n up because it's stuck on the bottom. All stuff we've done before, that's where this formula comes from. So, this is in a situation where they tell me they know how big of an error they want, but they don't know how big of a sample to take. For example, up here, how big of a sample did we take?
459.
No. 652.
Oh, shit.
What error did that lead to? 3.66%, yes?
Yes.
You with me? So if I were to do this formula and plug a 3.66 in and do all this shit, it would come out with 652. Because that's how big of a sample leads to that size error. So here, can anyone tell me blah, blah, blah. Oh yeah, okay, there's always, right. The other part of this is, do you see how I have to know these to be able to plug them in?
Yeah.
What if I haven't taken a sample yet? And that's the whole purpose, yes? I'm supposed to do this to figure out how big of a sample I need to take. But where do P hat and Q hat come from?
The population.
The sample,
Yeah, the sample.
yes? I haven't taken a sample yet. To figure out how big of a sample I need to have taken a sample. Shit. So, if you had no idea the percentage of people in the next room who are older than 21, on a college campus, there's a building 3 miles that way, yes? What percentage of the people in that building are older than 21? Do you have any idea? Without any information, what is your best guess? 50-50, right? You with me? Now, and listen, on one level that might be, because I don't know what P hat and Q hat are, correct? I need a best guess. So our best guess is 50-50. Mathematically, so you guys are with me, if I don't know something, should I have to take a larger sample or a smaller sample? If there is something I don't know,
Larger.
I should take a larger sample. Does that just generally make sense?
Yeah.
That's gonna become big, by the way, in section 8.2. So it's a good thing I'm saying, this makes sense. If there is something I don't know about what I'm studying, I should take a larger sample to be more confident, yes?
Yeah.
If I make P and Q both 0.50, 50-50, mathematically that makes N the biggest it can be. So on part A of number 2, I have not taken a sample yet, correct? I don't know what P hat and Q hat are. I don't have any numbers to do anything with. So I'm gonna guess 50-50, because that's our best guess, but also that makes N the biggest it should be, which makes sense. If there's something I don't know, I should be penalized for that. I should have to take a bigger sample. So, in the case that I have not taken a sample yet, and I need to know what P hat and Q hat are, you guess them to both be 50%. This is gonna happen in the homework, on the test, blah, blah, blah. Yes? Okay. So, if I plug that in, so I want 99% confidence, what is that gonna tell me? Z-score, is that in our baby chart?
Yes.
Yes. So if you look it up in the little baby chart, what do you get for the Z-score?
2.575.
Kick ass. What error do we want?
3%.
3%.
99%. Oh.
I want a 3% error, yes? I want to be 99% confident. What error do I want that to lead to? 3% error. Is that cool? Do I put 3 in for E then?
Yeah.
No,
No.
because 3% is some shit we made up. What is 3% really? What number is 3%? What number is 3%? What decimal? Yeah, 0.03. So my error to be 0.03. Up here, did we get 3.66? No, we got 0.0366, yes? Because that's what a percentage is. It's in decimals, and it's a way that we write decimals so it looks better to us. I'd much rather say 0.1% than 0.001. So now I've got, do I have everything I need for this formula?
Question really quick. The 50% is still catching in the middle, right?
What do you mean? Sorry. No. 50% is my best guess for the percentage.
Right, but like it's still catching in the middle for your Z-score. Like it's supposed to all be in the middle.
The Z-score is coming from 99% confidence. So I want to catch 99% of the data.
Oh, so then it's like whatever on the outside.
Yeah.
Okay.
So it'd be 0.01 on the outside, 0.005, and you could look it up, but it was in our baby chart, so we can get it quicker. So it's just a shortcut, right? Okay. So real quick. Our sample should get larger if we want our error smaller. Does that make sense? Okay, so we see that. If I make error smaller, I'm dividing by less, my sample size would get bigger. What if I want to be more confident? Should our sample size get bigger or smaller? Bigger. So yeah, if Z goes up, doesn't N get bigger? Okay, so you can kind of see the effects that these things have, and it makes physical sense. It makes real world sense, is my hope. So if we throw all this shit in, we're going to see all the effects kind of go together. I want to be this confident. I want to be within this much. What sample size is that going to lead to? So let's see, it'd be 2.575 squared times 0.5 times 0.5 divided by 0.03 squared. So just throwing all that business in there. The Z squared, P hat, Q hat, error squared. And now go ahead and throw all that into your calculators. Let me see what do I get? Whoa, holy shit, really? It's too much. Probably do that wrong in my head.
1,841.
Yeah. Sounds about right. 1841.84.
84.
Now, what is that supposed to be again?
How many people?
How many people? So what's wrong with that?
Can't have.
I don't want you to take, I only need 84% of you, chop. No. So of course we're gonna, no matter what the shit it is, we round it up. So I need 1,842 total people, yes? Okay. That is if I don't know anything. Have you guys ever heard the phrase preliminary study?
Yes.
So just one of many reasons we do that is, remember if I made P hat and Q hat both 0.5, it makes N the biggest it could be. So if I do a small scale study, I will get an actual P hat and Q hat, which might not but be 0.5. And then my N will be much smaller. So that's one reason why we do preliminary studies. So what if I did a preliminary study of only 42 students, yes? And I found that 31 of them passed the first time around. What's P hat now?
31 out of 42.
31 out of 42. Which is like 5 out of 7. It's like 0.7 something.
0.7380.
You guys get that? So then what's Q hat?
.2619.
Okay, 262. I like it. So we did a preliminary study. Up here we had to guess what P hat and Q hat were, yes? Because we had no idea. We had talked to nobody. So we had to guess 50-50. Now we have actual values for them. So now let's recalculate how big of a sample we need. Everything's going to be exactly the same except, of course, for these two values here, because now I know this is 738, and I know this is 262.
Wait.
What's up?
Forget the Z-score.
Oh, it's still the same. If we had done, still the same problem. It's just part B of the same.
Got it.
Yeah. So I want to be just as confident. I want to have the same error, but now I've got a preliminary study under my belt. I got some actual findings. I think it's going to be like 1,400 something. I don't know.
You do math pretty fast, man.
Huh?
So you move quick.
No, what is, I'm sorry.
1425.
What is it? Sorry? 1425? Is that after rounding up?
Yeah.
So you got 1424 something?
Yeah, 1424.52.
Chiboo! Now, real quick, on this example, I mean, they're both decently large numbers, but isn't this more than 400 less people that you have to talk to? And even beyond that, didn't we already talk to 42 people? So could you tell me how many more people? Because that's my real question. How many more students would we have to talk to? How many did we already talk to? 42. And they need 1425 total.
417.47.
What's happening? No. So I got 1425 I need. I've already talked to 42 people. I don't know if I heard you wrong.
Oh no.
1383 sounds right. So if I do a preliminary study, I'm already getting some information. Then when I see how large of a sample need, I can just subtract that off because I've already got that many. So it helps twice over. It cut my number I needed by 400, plus I've already got some people. Okay. This whole thing does the same thing the other confidence interval did that we made before. It's trying to give a better feel for what the true mean or the true percentage is by giving an interval. That's much better than me just saying a number. If somebody tells me, oh, it's 68%, give or take 2%, that's pretty good. 57%, give or take 10%, holy shit, man, I can't, that's a little much, that's too big of an error. Okay. Maybe. Alright, now. So the new things for today were this check, instead of n greater than 30, that's for means, np hat, nq hat, or np, nq, depending on what I have, that's for percentages. They both do the same thing. They're checking to make sure we can use the z-score chart by making sure the distribution is normal enough. Okay, maybe. We developed the formula last time, the same way we developed the first formula. Okay. So I do 8.1 and 8.3, and I skip 8.2 for the moment because 8.1 and 8.3 both use the z-score distribution. So it kind of makes sense to me just to stick with those two together. Today, right now, we're going to talk about, I've got another chart for us. It's so exciting. But I want to first, before I give it to you, I want to lay the groundwork about why this chart's needed, how it's related to Guinness. Somehow this is related to Guinness. Do you guys know what Guinness is?
It's a nice beer.
It's a beer. And the comedian said it's like a beer that somebody shoved a whole meal into.
Yes.
Yes. Huh? It's anyway, you don't have to go out and drink this stuff to understand stats, yes? Although some math was created by people that were under the influence of something. So there was this guy. His name was William Gossett. He was working for the Guinness Brewery. And I just love the word brewery because it makes you sound like you're already drunk. Or even the brewery. William Gossett worked for the Guinness Brewery. Part of the conditions for working with them is he did some research for them, which is neat. He wasn't bottling the Guinness, he was doing some research. Any research he did would become property of Guinness. So he had to do some research related to what we're doing now, these confidence intervals. But he didn't even freaking know what the standard deviation was of the population, the sigma. Now, real quick, you guys help me out. If this poor dude didn't know sigma, what's the next best? Look at that word. Just gaze upon that word. Look at this. What is that, Jeff? If he didn't know sigma, what must he use instead? What is sigma?
Standard deviation.
Of? So what must he use instead?
Population. Sample. P hat.
Alright.
I think we're all confused right now.
If I don't know the population mean, I would instead use the sample notes. If I don't know the population standard deviation, I would use the sample standard deviation. I need it to be a standard deviation, yes? I can't just plug any old, let's plug the mean instead of a, no. I need it to be a standard deviation. He was taking samples, and that's how he got data, correct? But he didn't know the actual population standard deviation. This is even more true to life. Most of the time, this is what it is. The thing with the spiders, if I found a new species, do I know anything at all about the population of that species? No. So in reality, we'd have to use S. Now, do you all agree that whatever S is, it is almost certainly not equal to sigma?
Yeah.
So right now there's a standard deviation of ages of people in this room. If I just took you guys and I got your standard deviation of you guys, I, being a teacher, will put a lot of money on your standard deviation being different from everybody. And the reason I say being a teacher is because we don't get paid enough. So it means a lot if I put a lot of money on it. You with me? Okay. So, the whole idea of a confidence interval is to kind of cover our ass. We try to go catch enough data so that we can be such and so confident. If there is a part of my formula that I don't know for sure, I've got to use an approximation. Should my confidence interval get bigger or smaller because of that? What's the whole purpose of the confidence interval? Why is it sometimes bigger?
That's bigger.
Because I want to be more confident about something. So, if there is a part of my formula for my confidence interval that I am estimating, so I don't know what the shit it is, what do I do to cover my ass for that fact? Is I make my confidence interval
5.
bigger.
Oh.
If there's something I don't know that I should normally know, I'm going to get a bigger sample to cover my ass for that, yes? Real quick, when does S approximate sigma better? When I have a small sample or a big sample? Big sample. Okay. So if there is a piece of my formula, and in fact, here's the formula I'm talking about. This is the formula we used before. Before William Gossett can't use this formula, because what does that formula require that he knows?
Sample size?
No, he's going to know that because he's taking the sample.
Standard deviation.
Yes, he does not know the standard deviation of the population, correct? That was the whole condition. So he's like, shit, I don't know what I need to know to use the only formula there is. So let me see if you guys, all right. For a given confidence level, so let's say I want to be 95% confident. If I go through all the shit and I know everything I'm supposed to do, it's going to make this big of an interval, yes? Let's say. You with me? If I want to redo that whole thing, but I don't know sigma, this should get a little bigger, yes? I should go a little further out. You with me? So for a 95% confidence interval, I would use 1.96 for my z-score. Can you guys double check? You never know. Could have went insane. Look at your little baby chart. 95% confidence, 1.96 z-score, yes?
Yep.
So, for William Gossett and for everybody else after him, if I don't know sigma, I gotta cover my ass a little more. I've gotta make this a little bigger. So I'm not gonna use 1.96, I'm gonna use maybe 2 point something. I'm gonna go out just a little further. Does that by itself make any sense at all? There's something in my formula that I'm approximating. Shit, how do I make up for that? I go further out. I catch up. So if there was a fish I wanted to catch and I didn't know how far he swam, I'd have to throw a slightly larger net out to maintain how confident I am I caught him. Does that make sense? Keep talking about fish, by the way. I hate fish, I don't like to fish. But it's kind of, I like the idea of throwing a net out. It's sort of like what did we do when we make an interval? We're throwing a net out. Okay, let me stop, yes.
So you're just making a random confidence level right now?
Well,
Because you
not a random one, but in a given situation. If I want to make an interval and I don't know this, I can't use this. See how these go together? So what he came up with are called T-scores. And when he submitted it, just to complete the history here, he had to do it anonymously. So he called himself student. So it's called a student's T distribution instead of a Z distribution, right? He wanted to do that because he didn't want Guinness to own it, this research he did. Let me stop for a minute. How important is the whole Guinness and the William Gossett knowledge? Not important at all, but just to add a little flavor to tell you where the hell this came from. It was some guy who had drank a lot of Guinness. So it sounds like, let's use it, sounds like it's probably good. So does everybody get the idea? If I don't know sigma and I use an approximation, I can't use the z-score, I've got to use a number that's bigger than it. The smaller my sample is, how certain am I that S is close to sigma if my sample gets smaller? Less certain, yes? So then the number I put in place of Z would be even bigger. Because the smaller my sample gets, the more I need my ass covered. Yes? So literally I think about like a towel and I'm like, I got a big ass, I gotta cover that thing. Yes? You guys kind of, no? Okay. Alright. If you're offended, too bad. So what I'm gonna do, so what happens then is we're gonna have a third, and this is the last one by the way, a third confidence interval formula, and it's gonna look almost the same as this one, except instead of sigma, we have to use S, and instead of Z, I must use T. So again, T exists just to push our interval out a bit. How far out do I go depends on how big of a sample I took. So somehow the chart I'm about to give you, the smaller the sample, the bigger the T-score gets. Because then I've got to cover my ass more and more and more and more, yes?
And this is if we don't have.
We don't have sigma. If we have sigma, we're back in section 8.1, I could use a z-score like always. Sorry. Yes?
Is this still chapter?
This is section 8.2. We're finally into the forbidden part of the library. We're taking a step in.
Still in the parking lot.
Okay. But of the right building, yes?
Yeah.
Okay. So does everybody sort of get the idea? Anything that I'm trying to measure that I'm not as certain about as I should be should result in kind of a penalty. I should penalize myself in a statistic. So in this case, for an interval, it's going to make it bigger. Because what kind of interval is the best? A small one. Because that means that's really kind of accurate. Yes, the error is small. So if there's something I don't know in my calculations, I have to make it bigger. I just have to. You can think of it either as catching more data to make up for that, or making it bigger to penalize myself because there's something I didn't know. Okay. Next thing that's going to seem disconnected, that I'm really happy right now that I remembered to talk about before I gave you this chart. Do you guys remember when we talked about n-1 before?
Yeah.
Because it was the difference between the standard the variance for a population and the variance for a sample, yes? It was this little dude at the bottom. I cannot currently remember how much I spoke about this, but if I take a sample, I'm pretty sure I talked about this more than normal with you guys earlier. If I take a sample and I get a sample mean, is it going to be the same as the population? Almost definitely won't be, correct? Isn't there a number I could add to my list of data that would make it the same? So that's where n-1 comes from. It's kind of going, there's one data point you don't know, the magic one that would make it the same mean. Another way to think about n-1, and I'm pretty sure I talked about this before, but just to remind you guys, if I have three numbers that average to be 30, what do you know about, I'm sorry, three numbers, sure, I will go with it, I already said it. Three numbers that average to be 30. Do you know anything about any of the individual numbers? I don't have a clue. It could be anything. But what do they have to add up to be?
60.
90.
9. Because how do you get the average of 3 numbers? You add them up divided by 3.
Got it.
If I get 30 when I do that, they must add up to be 90. Yes? Because only 90 divided by 3 is 30. You with me? How many of those 3 numbers could I just, without even thinking, make up before I had to get serious? I could make 2 of them up, yes? So how many, what's my n for this? What's the n? 3, yes? And how much freedom did I have? 2. So we call this the degrees of freedom. And I can't help but say it like that because I watched Braveheart, so. I don't know if you guys saw Braveheart, but that's okay if you didn't. It's got weird ass dude in the lead, but we'll go. So on this chart, you're gonna see DF, and that means degrees of freedom. Yes. Okay, so let me give this to you, and then we'll talk about how the hell to read it. Okay, it's got the same color scheme, which I don't know if it's good or bad. All right. Can you guys see? Actually, I'm sorry. It says more than DF. It says actually degrees of freedom. That's nice. Up top is some weird shit. Yes. Okay. Can you guys here just to kind of get into this chart? Can you guys draw a representation of a 90% confidence interval? Everybody take a moment. Given a normal distribution, draw a representation of a 90% confidence interval. So it catches the middle 90%, yes?
Yep.
So everybody should have something like looks like this to some degree. When I chop this off, do you see how I made a certain number of tails? How many tails did I just make? 2. The symbol that we use for the area in the tail or tails is alpha. The nice thing about alpha is, what letter of our alphabet does that Greek letter correspond to? A. And A for area.
Yes.
Also, it's supposed to represent the area in the tails, and what does it look like?
Fish.
They have tails. Good. So we have a symbol. That's the Greek letter A for area, and in the area in the tails, it's a little fish dude. So you almost can't go wrong. Put a little eyeball in if you want to. Okay. So alpha is the area in the tails of the picture. So what is alpha in this problem?
90.9.
No, where's my tails?
Oh.
Where on the picture are my tails? This is the body, yes? Where are my tails?
0.5.
Here.
It's 0.005.
You guys with me? Do you guys all agree? When I chopped it off, I made 2 tails, didn't I?
Right.
They're the ones on the outside there. What area is in the tails?
0.10.
Yes, 0.10. Kick ass. Stop.
It's a total, right? So, sounds like maybe.
What area is in half of the tails? Is in 1 tail?
0.5.
In the book, you might see this symbol.
Right.
That just means the area in 1 tail. Yes? So now if you look back at your T-score chart, let's do this. Let's say I want to be 90% confident. And I have n equal to 46. First question I have for you is, what's the degrees of freedom? 45, I like it. Second question I have is, now here's what's kind of nice at the moment. No matter which way you look at this, how much is in two tails? What area is in two tails? How much area is in two tails for a 90% confidence interval?
0.10.
0.10, you with me? Isn't that two tails, yes? Two tails? 0.10 here, right? What area is in one tail?
0.10.
No. What
Oh,
area is in
0.5.
one tail?
0.5.
105. Is it the same stupid column, yes?
Yeah.
Okay, so for confidence interval, we always make two tails, correct? So at the moment, it doesn't necessarily make sense why they put these two rows. I'm going to talk more about why the two rows there in a minute, but for right now, you almost can't go wrong. Which way you look at it, it's the same column. Now, where do I want to stop in this column? What's my degrees of freedom?
45.
45. Jeff, put your glasses on. There we go. So I stop where? 45. And what do you guys get? 1.679. Sweet.
Wait a minute.
What's up?
Oh, a minute.
Now, real quick, can somebody look at your baby chart? If this was a problem where I was allowed to use z-scores, what z-score would we use for a 90% confidence? 90% confidence. 1.645. What's true about the t-score we just got? It's a little bigger. It's going to cover my ass a little bit because there is a part of the formula we're using an approximation for. It's going to go, oh, okay, I got you. And look what happens. What happens to the t-score if my sample size gets smaller? So I'm going to go up. What's happening to my t-score? Because if I have a smaller sample, I need to have my ass covered more. Because now I'm even less certain about how good S approximates sigma. So again, the bigger my sample, the more certain I am about anything I get from it. The less help I'm going to need from T to cover me for not knowing something. In fact, what happens when your sample gets really large? Look at the bottom of that column.
Goes up.
Very bottom, when your sample is, and you gotta love the fact that they actually do say large.
Oh, goes down.
What does it become exactly? Does that number look familiar? That is the what? You can do it. That is the z-score, yes?
Oh.
Do you see 1.96? So when my sample size gets large, now real quick, side word about large. Why did they put the word large? Because it depends on the situation what large enough is. But you see at the point of 2000, aren't I already, if you look at those numbers, aren't those already really close to the actual z-score? I want this to make sense. So if I have a big ass sample, I could just go ahead and use my z-scores because I feel really good about the S that I get. It should approximate sigma really good. Do I need somebody's help to cover my ass? Nope. I don't need as much help. I don't need any help. I'm good. But as my sample gets smaller, oh shit, I'm not as sure about S approximating sigma well. I need to kind of cover myself for that fact. So the funny thing is, the only thing that materially changes is instead of looking up the score on the z-score chart, you look it up on the t-score chart. All of the actual work is the same. The formula is almost the same. You calculate your error, blah, blah, blah. You just don't put in example, you don't put 1.645, you put 1.679 instead. And then you just do all the same math you would have done. Maybe? So this has happened a lot to us where Jeff takes forever to freaking talk about an idea. And then the actual effect it has on your work is very minimal. Now, I don't know how you feel about this chart. This chart, I feel like it's easier to read than the z-score chart was when you first got it. I don't know if you guys agree, but most confidence intervals, I would look at them as two tails, but it's really up to you. So which column would I use if I wanted a 98% confidence interval? What's the alpha if I want to be 98% confident? What's alpha?
0.02.
Mm-hmm.
And then
So which column am I going to use?
Second column.
Second column, because that would be 2% in two tails, yes? What if I want to be 80% confident?
What do you owe the fifth column?
Yeah, the last column, because if it's 80% confident, it must have 20% in two tails. Now, I told you I'd come back to this. The next thing we're going to get into after this, obviously we're going to do examples of this. The next thing we're going to get into this is testing claims. This is the whole thing about it's been clinically proven. We're going to see what the shit goes into clinically proving something. Yes? We're not going to suddenly do experiments. I'm really sorry. You're not going to be pouring acid over stuff. If you wanted to do that, there's classes. They have stuff. You can pour acid. Be careful. But when we get there, our claim could be, I think that the average time to relieve a headache with my new medicine is less than the old. Yes? In which case, I just have one tail. For you guys, it would be less than. So that's when we get to hypothesis tests, the one tail, two tail breakup is going to make a lot more sense. It's going to depend on our claim. Is our claim that it's less than? That's one tail. Is our claim that it's different? That would be two tails. It could be up or down. Okay. So let's try. Let's see. Oh, here. Let's do this. You guys, when you get the sheet, try the first two problems. Mean by 1A and 1B.
Jesus.
No CGs. So hopefully it makes sense. Z or T, I still need a normal distribution, right? T is just kind of pushing Z out a little bit, so it still needs a normal distribution to work. So for part A, what's the degrees of freedom?
5.
Good, it's just always one less, well, not always, but for us right now, it's one less than the sample size. When we have more than one sample, for example. We're not there yet. Sorry?
So we're just subtracting 1?
Yeah, because what's the formula for the degrees of freedom? It's n minus 1. 99% confidence means what percentage in two tails?
0.
0.01, and I want to stop at
5.
5. So then the t-score we would have to use is 4.032. Do you agree with me that's pretty big? Why is that not surprising?
Because your sample's small.
Sample size is so damn small. The math is like, okay, human, what the shit? You're gonna have to go way out. So 4.032.
Show that again.
Sorry?
You might try that again.
Okay, so degrees of freedom, 1 less than 6, so 5. The 99% confidence means there's 1% in 2 tails, yes? So then I just stop at 5. So here's a thing I like to say. If you stop, you get a t-score. If I go all the way to the bottom, I get a z-score. Now this actually improves, you guys, we just did a 99% confidence interval earlier, didn't we? It was 2.575, does that sound familiar? Do you see how this one says 2.576? That's actually a little more accurate. But I mean, these other ones should look very familiar, 1.645, 1.96, that's almost 2.575, right? So at the bottom are z-scores. What's the degrees of freedom for part B? 100. 90% confidence means how much outside? Or how many in 2 tails?
0.10.
0.10. So I want to use this column here. And I just want to stop at 100. Yeah. So I get 1.660. Is that what this says?
Yeah.
Yes. Jeff. Alright, now, I left the last one to do with you because it gets a little tricky. Doesn't seem like it should, but do you see how this chart takes big steps as it gets further down?
Yeah.
So in general, if I have a degree of freedom that doesn't show up, so what's the degrees of freedom for this officially? 92. Do we have 92?
No.
No. So we have a chart that doesn't give us the specific information for that situation. I should penalize myself. You always go numerically the next thing down, so 90. Chart-wise, the next thing up. Do you see what I mean? It always gets confusing when I say you go down, but that means from 92 you go to 90. Here you go up to 90. So I'm going to have to use 90, that's the next best thing. And then if I go, what's my area in 2 tails? 0.02. So I'm going to use this one. And I'm going to stop at 90. So I get 2368. So again, in each of these situations, if I had to construct a confidence interval, I would put this number in place of where I would normally put a z-score. Yes?
If it was 96,
You would still go to the next one down.
so 100 or?
You would go to the next one down.
Okay.
If it was 99, and I'm not going to be crazy critical about that, but you really should compensate. You should be, what's the right word? Starts with C. You really should be conservative. You should kind of make the number go up if you don't have the exact thing you need. Okay. So, if I want to use a Z or a T, I need a normal distribution. Yes? I either have to tell you that, or what else would tell you is normal enough?
30 above 30.
And greater than 30. So, number 2, can you guys look through these real quick? Which one of these would I not be able to do?
C and A.
Well, A is okay. Why is A okay?
Oh, because it says probably.
Sample size doesn't save me, but did I need it to save me? It's already normal, yeah? What's wrong with part C?
Not
It's
normal.
not normal.
It's not normal. Does the sample size save my ass?
No.
Nope, it's not big enough. So part C, in this class, we couldn't do anything.
So, in it.
This has to be more than 30 or 8%.
Has to be more than 30, exactly.
I like it.
So this is the one can't be done. So I've already told you these other three can be done. So go ahead and do those.
So you would just read this as the question on the test, you just write it down.
Like I said, in stats 2, you would learn some methods to do some stuff, but we don't offer that. And just to kind of hopefully help you guys out, there's a really nice thing. You're not allowed to use notes on the test, but I'm going to point out something about the formulas. But for right now, why were T-scores invented?
To replace S.
Because some guy drank too much. No, because, exactly, if I don't know sigma. So if I have a normal distribution, when must I use a T-score if I don't know sigma, correct? So in part A, is it normal? Yes. Check. Do I know sigma? Check. So therefore, what can I use?
The score.
Z or T? Z. Because T-scores were invented for situations where I don't know sigma, where I only know S. Yes.
So that's how you answer that question. 'Cause that's where I have problems sometimes, and sometimes I know how to do like the math stuff, but I don't know how to answer the question.
Oh. Okay. Well, I'm not done with it, am I?
No.
So, the excuse me. The first level of this problem is it a Z or a T score? The second level is find that score. So here's what's beautiful. I don't know. Let's see if you guys are cool with this. Today I gave you a brand new chart. Yes. What does that chart have on it? That's so amazing. What do those numbers represent? T-scores. But at the very bottom of each of those columns lives what kind of scores? Z-scores. I don't know if some of you guys realize this, but it's kind of like an upgrade to the baby chart. So if I want a Z-score and the confidence level is on there, I could use the T-score chart. I just go all the way down. So if I go all the way down, I get a Z-score. If I stop somewhere, I get a T-score. So I want a Z-score. What's the area in two tails for part A? How much area is in two tails? There's 90% inside. 0.10. So you know which column to look at, and I want a Z-score so I just don't stop. There ain't no party like a Z-score party.
1.645.
Yeah. You guys see that? At the bottom of the 10%, let me show you. 90% confidence, I want 10% in two tails. If I go all the way to the bottom, 1.645. Or you could use the baby chart, right? Doesn't matter.
That satisfies the answer.
Yeah. So I wanted to know Z or T or can't be done, and then find whatever score. So try part B. So just make sure you guys are cool with this. The population is not normal, correct? Why are we okay though?
Because it's more than 30.
And greater than 30. So it is normal, check. So it's gotta be normal to do anything. And then you say, which score do I need to use? And what actually determines Z or T?
If it's an S or.
Beautiful. Just which standard deviation do we have? That's it. So am I gonna use Z or T for this? T score, because I just have an S, I don't have sigma. Yes?
So S is sample standard deviation.
Of course, yes. So in the beginning we knew sigma was population, it was a Greek letter, S, R letter, sample. So I know I'm gonna get a t-score. What do I have to know to be able to get the t-score? Two things, yes? What's my alpha? 0.02. So that's the area of two tails. And what is my degrees of freedom? 38. Good. So that's all I need to know to figure out what that t-score is, yeah? So I know the area in two tails is 0.02, so I'm gonna go here. And I'm gonna stop at 38. That's my degrees of freedom, so I'll just go down, stop at 38. Shoo-hoo. So I get 2.429.
Yeah.
If it was a z-score problem, I would use 2.326. Since I don't know sigma, I just know s, I have to penalize myself a bit and go 2.429, go a little further out to make up for that thing I don't know. That is desperately trying to be a 9 there.
And then if it was like 90 or 105, you would go down to 100.
Yes.
Okay.
Good. What about part D? Is that one I could do?
Yeah.
It's like doubly over good, yeah? Population was already normal, but the sample size was ready to save me. But I'm like, thanks, Tim, I'm good. So I know I could do something. It's normally distributed. What determines Z or T?
The S.
Which standard deviation I know? In this case, I know S, which means I have to use what kind of
T-score.
a t-score. Okay, so go ahead and figure out what alpha is, look at the right thing, stop at the right place, all the stuff. Do it, don't say anything. So we got alpha is 0.01. Degrees of freedom is 60. 0.01 is the first column, and I just stop at 60. So I get 2.66. Which is a math person, I just love that there's a 1.66. So that's okay. Yes.
So for number C, there's no intended getting.
Which one, sorry?
Number C,
For part C?
there's no intended getting the calculation of rate.
Yeah, it wasn't normal. Now up here, for example, we did this one, even though that's not greater than 30, because it was already normal. Or it's not normal, but the sample size stays. This one, it wasn't normal and the sample size wasn't bigger than 30, I can't do anything. Yeah. Okay, maybe. So we really didn't learn a new formula, we just learned a different number to put in instead of Z. It's really the same formula. So here are the 3 confidence interval formulas that we know. The first one we learned was this one. The one we just learned today is this one. And the one we learned last time and we used earlier today was this big ass one here. They all have the same kind of structure. So if I asked you on a test, construct the 90 whatever % confidence interval you know it's gonna be one of these three. They're the only ones that have the plus or minus in them. That's the only way I can make an interval is to go up and down some amount, yes? I always get people use this formula in all these weird places, and I'm like, no, you only use these to make a confidence interval. That's what they do. Now, you're not allowed to use notes, but you see how the formulas tell you use this when you know that, use this when you know that. So they're notes. The formulas are very often notes. Okay. Maybe? And you guys seem really excited about this. I'm sorry. Yes.
Wait.
No, you don't have. It's okay.
Love it.
Who knew statistics got boring sometimes? So what I want to do, I want to do number 3 with you, and then I at least want to talk about the back. Let's see, because look at the back. This. Ooh, look at that! Look at that! Gaze upon. Okay, come back. Sorry, sorry. So real quick, does everybody have their calculator ready? So here's what we can do now. I can be just given a pure set of data and nothing else. Because now we can calculate X bar and S, and I now have a way to get a confidence interval just knowing that. I don't have to be given much information, just have to be given pure data, which is more real to life. So can everybody take a moment, put this into list 1 in your calculators. All I need you to do once you get it in there is to get the mean and the standard deviation, and I kind of told you here how to do it, but how do I get to 1 bar stats? Does anyone remember? Stat, calc, 1 bar stats, L1. Take this out because I just have this. Jeff, you're amazing, Jeff. Let's try this again. Take out list 2, delete list 1. There you go. I don't have a frequency list, so I take list 2 out of there in case you had it in there. Then you calculate. Let's see if we all get the same stuff. What's my mean? Yeah, 78.286. Then my standard deviation.
13.724.
Good. Can somebody remind me? Do you see how it gives me 2 standard deviations? We're the humans. We have to know how the hell to use it. The calculator's dumb. It's just going to calculate both of those at the same time because it has no idea. We're the humans. We're like, oh, I know it's a sample, so I'm going to use this guy. 15.724. And what's the key thing that tells you you can do anything here? Because how big is our sample? 7. So why am I allowed to do anything? Yeah, I tell you it's normal. So now I can look up the z-score. I'm sorry, kind of giving away the game here, but which score do I need to use? Not the z-score. Yeah, why do I need to use a t-score? I only know S, yes. So if what's my degrees of freedom? Good. 7 minus 1 is 6. What's my alpha? What did I say? Oh, it's down here, Jeff. You're trying to do too much up here. Degrees of freedom is 6. My alpha is going to be for 98% confidence. What's alpha for 98% confidence? 0.02. It's just the area that would be outside. That's all. 98% in, 2% out. And then if I look up the t-score, I'll go to 0.02 column and just stop at 6. So I'm going to use 3.143. And now I can just plug and chug. So it'll be 78.286, give or take this many steps. Where'd it go? There it is. By the way, 2 things. it's really easy to put a 6 there instead of a 7 because you just calculated the degrees of freedom, but it's gotta be n. It's gotta be the real sample size. Secondly, I always get people confused about this. Do you see I'm dividing S by square root of n? When I divide by the square root of n, I'm not taking a population standard deviation and making it into a sample one. That's not what that does. Sigma and S are both spreads of individuals. I need to change both of them to become spreads of a group of whatever size, in this case 7. So I still have to divide by square root of 7 to make it become the right spread number that I want. So obviously, almost always, setting up the formula is the hard part. Now we just figure out the error, add it, subtract it, right? Same stuff we did before. So figure out what this here is. 17 points. 18 points. Okay. I'm doing it in my head, so I'm gonna be on. I'm okay with that. So 78.286, give or take, how much? $18.6792. Neat. Oops.
Wait, how come it's 3.143
Huh? Oh,
for the t-score?
so alpha is 0.02.
Mm-hmm.
Degrees of freedom is 6, so I go to 0.02, stop at 6,
Oh, I
and you get
forgot to do
3.143.
Yeah, probably.
And then here, I got 18.679. So what you guys got? Yeah? 92, sure. Okay. 6792. I guess so, because I went out 3 places in this like a madman. And now you just subtract that and add it. It becomes something that's very not useful. So I get 59.61 roughly up to 96.97. This is an estimate for the true mean grade in a class. Why is this not useful? Because we're saying the true mean grade is anywhere from an F to an A. It's like slow clap time for that.
Good job, statistician.
Why is it not our fault as a statistician doing this analysis? Because he only gave me 7 bits of data. How the shit, what do you expect from me? I'm not a miracle worker, right? So that doubly did that. That low sample, we don't know sigma, using a bigger score instead of z, and also I'm dividing by a smaller number because of a small sample size. I'm doubly screwed. This is gonna be a big ass confidence interval. Not our fault. Bless you. Maybe. Maybe. Alright, so obviously, I'm not gonna have time to make you do this. I'm gonna try to do this first thing next time. This wall of data, I think I told you this before. If I want you to make a 90, if I'm gonna have every single person in here make their own 90% confidence interval, what percentage of you should end up not catching the real average? 10%. So we can actually see if that happens. If enough of you show up next time. Yes? To get over how much I bored the shit out of you today, please come back next time and we'll be able to get a better result with more detail. Okay. See you next time.
Papers and folders and shit.
Thank you. Oh, yes. in the,
I think before that,
oh, no, cause you got the worksheet for it, right?
yeah.
Okay, you're good.
So this is really late. A lot of my work is I'm trying to go
Oh.
to 2 minutes.
Put your name on it.